So, this will be a series of lectures on galaxies and their aggregates, groups, clusters and superclusters. In the first lecture, we have divided it into small parts. The first part will talk about how the universe is made up of galaxies, just as matter is made up of molecules. Galaxies are the fundamental building blocks of the universe. Now, we did not know this more than 100 years ago. In fact, if you look at the sky through the naked eye, you see something like this, or through a small telescope, and all you see are stars in the sky. But if you look through a big telescope, or say the Hubble Space Telescope in space, you see something like this. And in this picture, there are only two stars, up there and another at the edge of the picture. Almost all the things that we see in this picture are galaxies, and each galaxy has 10 to the power 11, 10 to the power 12 stars. So, these are the things that make up the universe, and here we see these stars that belong to our galaxy. We did not know this for a long time. In the 18th century, people started looking through larger telescopes, and they figured out that not all stars in the sky twinkled, and also they were not point objects. In fact, many of the stars, or so-called stars in the sky, were extended objects, fuzzy objects, nebulous objects. And these nebulous objects later became called galaxies. But if you look at these nebulous objects, you would find that they are not all the same thing. So, when these nebulous objects were being catalogued, and here is one catalog that a lot of people use, a catalog compiled by Charles Messier. I have taken 4 of these objects from this catalog of things that are not point objects, and I put it here to show you from modern pictures how different these things can be. There is, for example, the first one, which is M1, the Crab Nebula, which is actually a single star that exploded 1,000 years ago, and now it looks nebulous because it has expanded to form a very large nebula. Then we have a cluster of stars that has 1,000,000 stars in it, but through a small telescope it looks nebulous because you do not see the individual stars. You have a planetary nebula, which is something that is an evolved star that is quite old and has lost a lot of its matter, and so we do not see the star that is in the middle, but we see the nebulous gas around it. And then we have something which is a galaxy at this end, which has 10 to the power 11 to 10 to the power 12 stars, and this is a whole system by itself. Now, they all appear the same in the sky, roughly the same size, because there are different distances, and I put the distances there and the size of the object on the sky to show you that if something is very far away, it can be very large but yet appear to be the same size. And this is why till the beginning of the 20th century we did not quite realize how far away these things are, and so how big these things are. It was around the 1930s that we realized that there are some of these nebulous objects which are like these, which are very, very far away. They are millions of light years away as opposed to thousands of light years away, and thus they are the galaxies that the universe is made up of. Most galaxies in the universe look like this, about 3/4 of all galaxies, including our own galaxy, as we shall see. These galaxies are about 100,000 light years in diameter. In astrophysics, we use a slightly different unit. We use the unit parsec, which is 3.26 light years. So this galaxy would be roughly 30 kiloparsecs, 30,000 parsecs across. There are many other kinds of galaxies. For example, you have these, which are nice and round and ellipsoidal galaxies. They are called elliptical. About 20% of all galaxies are like that. You have the grand design spiral galaxies. Spiral galaxies have lots of spiral structure in them, and some have even bars in the middle. There are various different kinds of galaxies, and we'll look at some of these in great detail in the next few minutes. Galaxies don't like to live on their own. They often are found in small groups. Here's an example of a small group called Stephan's Quintet, where you often find galaxies interacting with each other when they come very close together, and we'll talk about that later on. Galaxies interact with each other, they cause each other to form stars and cause various other dramatic effects in other galaxies due to this interaction, and they often can even merge with each other. Now, early on, when galaxies were first discovered to be the building blocks of the universe, Edwin Hubble, who determined the distance scale of the universe and thus figured out how large these galaxies were, arranged all these galaxies in some kind of a configuration to imply how galaxies evolved. Now, this is a very standard thing that you might find in textbooks. It's called the Hubble tuning fork diagram, in which at one end you have the elliptical galaxies and the other end you have the spiral galaxies. And so these are called the early type galaxies and these are called the late type galaxies. And because in a tuning fork pattern the spirals are split into two, they are the barred galaxies on this side and the non-barred galaxies on this side. Now, this was done in the 1930s and 1940s. With the current knowledge of galaxies, we know that this is completely wrong, even though this is found in most textbooks. Hubble thought that galaxies form in nice round shapes, and as they age, they become more and more complicated and grow structure in them. We now know that galaxies form in flat disk-like systems with spiral structure in them. These are the young galaxies. And as they grow older, they merge with each other to form these nice round systems. So these are the old galaxies, these are the young galaxies. Evolution goes that way. And barred galaxies are not special, because all spiral galaxies, disk galaxies, grow bar instabilities in them from time to time. They are short lived, so at any given time you can see many of these disk galaxies to have bars in them. So you do not need to distinguish between them as two different things. I say this because this is our modern view of something that is embedded in most astronomy textbooks. The latest Hubble galaxy classification, Hubble type galaxy classification based on multi-wavelength observations of galaxies is far more complicated. As you can see, there are far more types of galaxies in the universe than that very simple classification that Hubble did. And I will later come back to talk about the constituents of galaxies and how the various components of gas, dust and stars give rise to the different kinds of galaxies. Let's summarize. We use the basic distance unit in astronomy, 1 parsec, 3.26 light years. And this actually happens to be the average distance between stars. Our nearest star is about a parsec away from the Sun. The size of a normal galaxy, at least the bit that we see, the stellar part of the galaxy, is about 30,000 parsecs or 30 kiloparsecs large. And it turns out that the average distance between galaxies is 1,000,000 parsecs, 1 megaparsec. Our nearest galaxy, the nearest galaxy to the Milky Way, is about 0.7 megaparsec, but the average is about a megaparsec. So now we take a look at our own galaxy, which we call the Milky Way. In other Indian languages, it is often called Akashganga, the river in the sky. Now, we live in this galaxy, so we cannot take pictures of this galaxy. But here is a way of looking at it. Here is a side view of this galaxy. I told you we live in a spiral galaxy, so it's a disk galaxy. And here it is a disk in which we are not at the center. The sun lies off center, but not quite at the edge of the galaxy, but it's in the disk of the galaxy. And you can see that if you are in the disk and you're looking towards the center of the galaxy, you will see that in the sky there is a band of stars, and that is known as the Milky Way. You see the Milky Way as a band in the sky. If you're looking away from that band towards another direction, then we see only some stars in the sky randomly distributed, right? And around this galaxy we have lots of clusters, globular clusters, that we can see randomly distributed in the sky from the point of view of the Earth. And in the middle, in the disk of the galaxy, you see a lot of dark dust. This is a byproduct of the formation of stars, and this dust obscures normal light, but it actually glows in infrared light, which we will see later. But this makes looking through the disk of our galaxy difficult. If this is a view from the top of the galaxy, not from the side, we can see that it's a flat galaxy which has at least 5 spiral arms, and the sun lies near one of these spiral arms, and the sun is going around the galaxy about 8 kiloparsecs from the center, which is 8,000 parsecs, about 25,000 light years. Now, this is what the Milky Way looks like from inside. As I told you, it looks like a band along the sky, and here we can see some of the dark patches, which are the dust patches. This is a picture taken from Chile, from northern Chile, from the Cerro Tololo Observatory. A lot of us work in these telescopes that are on top of mountains in the middle of the Atacama Desert in Chile. You get a glorious view of the Milky Way from the southern hemisphere, because from the northern hemisphere the Earth blocks most of the center of the galaxy. Here's of course a telescope, the 4-meter telescope in CTIO, which is now called the Dark Energy Telescope. And here you see 2 little systems which you don't see from India. We don't see these from the northern hemisphere. And these are called the Magellanic Clouds, the small Magellanic Cloud and the large Magellanic Cloud. And these are our satellite galaxies, galaxies that are much smaller than the Milky Way, but they go around the Milky Way. And I'll talk about our satellite galaxies in a moment. But you can now see what the Milky Way looks like from inside. Now, you can see other galaxies, and I call them the relatives of the Milky Way because they look very similar to our galaxy, but we can take pictures of them because we are outside them. And so here is a galaxy that looks very much like the Milky Way, and if you turn it around, here's another galaxy. It's not the same galaxy, but another galaxy turned around, and you can see this is what it would look like, another galaxy that's like the Milky Way from the side. And you can see this is exactly, if you focus on that, that's what you see when we take pictures of the Milky Way, right? So there are a lot of galaxies that look like the Milky Way that are spread around the universe. Almost 3/4 of all galaxies are like ours. And this one shows a schematic structure of what we saw before, which is the top view of the galaxy. As we can see, we have these spiral arms. Along the spiral arms, you see these little clouds, and these are called molecular clouds. These are made of molecular gas, and this molecular gas is at a temperature of a few hundred Kelvin, and this molecular gas collapses to form stars. So normally you see star formation in spiral galaxies along the spiral arms where you have these clouds of molecular gas. The Sun was formed in one of these molecular clouds 4.5 billion years ago, and now it is moving around the center of the galaxy. But there are other stars that are being formed in these molecular clouds now. Our galaxy is not a galaxy that is spectacularly forming stars. It has a star formation rate of about 1 sun per year, 1 solar mass per year. But there are other galaxies where there is more star formation going on, as much as 40 times or even 100 times more than our galaxy. Now, we will do a little exercise to figure out how the Sun is moving through our galaxy. You can see that that's the Sun, which lies, as I said, about 8 kiloparsecs from the center of our galaxy, and it's going in a more or less circular orbit. And we'll try and calculate how long it takes for it to go around the center of the galaxy. To do that, we know it's very simple. It's a circular orbit. We know that it's traveling at a speed of 220 kilometers per second. That's the unit that astronomers use for velocity. And we assume it's a circular orbit, and the radius is 8 kiloparsec, where a kiloparsec in kilometers is 3 times 10 to the 16. Okay? So if it's going in a circle, it's very easy to calculate that it will take 2 pi r, which is the circumference of the circle, divided by its average speed, and that will be the time taken. And if you use the right kind of units, we know that a year is roughly 3 times 10 to the 7 seconds. We use these numbers to figure out what this time will be, and it will come to be about 0.7 times 10 to the 16 seconds, and that comes to be about a quarter of a billion years. And this means that in the age of the Sun or the Earth, which is 4.5 times 10 to the 9 years, as the Sun goes around the center of the galaxy, and as it's gone around 20 times, it has also gone up and down perpendicular to the plane of the galaxy as well. And as it goes through the plane every time, there is an effect on the Earth's geological history that can be seen in various formations of rock, as well as the geological record in the ice in the Antarctic, for example. We now believe that it is possible that through one of these passages through the plane of the galaxy, the tidal interaction due to it caused a lot of activity to happen near the Earth. A lot of meteorites might have struck the Earth at one point, and this might have led to the extinction of the dinosaurs. This is a theory that is believed by a lot of the geologists who are working on the Earth's fossil record. In the next part of this story, we will look at what's outside the Milky Way and our immediate neighborhood. As I said before, the galaxies often are found in groups. They're often found in small groups, but they can be large groups which are called clusters, which might have thousands of galaxies. In our case, we belong to a very small group, which we call the local group, which consists of 2 major big galaxies. One is the Milky Way, which is our own galaxy, which we have already seen, and the other one is called the Andromeda galaxy, M31, which is of similar size to the Milky Way, and they are separated by about 0.7 megaparsecs. That's about 2 million light years. Now, each of these galaxies has a bunch of satellites around them, and we're discovering these satellites all the time. Right now, we know of the order of about 40 satellite galaxies for each of these galaxies. And if you look at them, here are they. So for example, here is the Milky Way with a lot of these, some of the prominent satellites marked, and you can see the two Magellanic Clouds, which we have already seen marked here, as well as some of the other galaxies. These are all much, much smaller than the Milky Way, just like satellites are for planets. These are called satellite galaxies. There are moon galaxies. They're much smaller, and we often call them dwarf galaxies. And then on the other side, we have the Andromeda galaxy, which also has lots and lots of dwarf galaxies around it. And these two galaxies are coming together, falling towards each other, even though the universe around them is expanding, and eventually they are going to merge with each other, which we will see towards the end of this lecture. So we look at some of these galaxies. Here is a picture of the Milky Way seen from inside, and this is a picture of the Milky Way seen in the infrared, and that is why we see the dust in the plane of the galaxy glowing. And what we see here is that the two Magellanic Clouds that we saw in the picture from the observatory in Chile before, just below the disk of the Milky Way. So these are our prominent neighbors, our two closest big neighbors, even though they are 100 to 1,000 times smaller than our Milky Way galaxy. If you close up on them, these are Hubble Space Telescope pictures of the large Magellanic Clouds. You can see that they are very irregular in shape. They are not the spiral type galaxies that we see. Most dwarfs are very irregular, even though here there is a prominent bar in the middle, and there are all kinds of star forming regions, nebulae. The 30 Doradus Nebula is very famous because there was a supernova in it in 1987, where supernova 1987A, which we could see even with the naked eye from the Earth. The Large Magellanic Cloud on the sky is larger than the full moon. This shows the scale of the galaxy compared to the size of the moon. We don't see it from the northern hemisphere, as I said before. If you happen to be in the southern hemisphere and you look up, you will see a cloud that is larger than the moon, and it will not go away because it's actually a galaxy that looks like a cloud. Its companion, the Small Magellanic Cloud, is also the same size of the full moon, and it is a little bit smaller than the Large Magellanic Cloud, and it is also seen with the naked eye. Not all of the other satellites can be seen with the naked eye. You need telescopes to see them, and some of the examples are these. Some are very easy to see with a small telescope, like NGC 6822, but some of them, like the Fornax dwarf for example, is very, very difficult to see even in very deep pictures, and it comes up as a smudge in normal pictures, and you need very sophisticated image processing techniques to find out that there is a galaxy actually there. These are some of our neighbors, some of our satellites. The local group then consists of just these two bunches, and both of these groups are coming towards each other. There are a few outliers, stragglers, that don't belong to either of these two groups. They are also dwarfs, but in the end, when the entire local group comes together, they will all merge together into one single big galaxy, and that will happen maybe about 4 billion years from now. Now, what we are doing to find these dwarf galaxies, more and more of them are being discovered, is we are now using very advanced image processing techniques from sky surveys to figure out where there are overdensities of stars in places in the sky that will be seen as a galaxy. Otherwise, they will be missed if people look at pictures of the sky because their surface brightness is very, very small. And this is often done from what is known as the Sloan Digital Sky Survey, the DR7, the data release 7 of the Sloan Digital Sky Survey has been used extensively for people. This was a sky survey for galaxies or known galaxies, but it has pictured about a third of the sky in exquisite detail with lots of digital CCD cameras, and there are lots of people who use image processing techniques to find from the stars whether they can find small but very extended galaxies that will be very nearby and satellites of the Milky Way. And in one of these searches this was found, for example. It's called the Sagittarius dwarf, and here what we have is that it's an enhanced picture of the Sagittarius dwarf galaxy. You would think that the dwarf galaxy would be a compact object in the sky like the other ones, but all of the purple in this picture belongs to one galaxy, and what's happening here is that our galaxy, the Milky Way, is drawing it in, and as it is falling into our galaxy, it is being stretched tidally all around the sky. So here's a galaxy that's been broken up, a small galaxy that has been broken up by our galaxy, and this happens all the time. Small galaxies fall into larger galaxies. These minor mergers cause a lot of the evolution of these galaxies. Here's one in action that we see. By no means these are unusual. Here are a lot of other tidal dwarfs that are now being discovered from these large sky surveys like the Sloan survey. And here are some examples where in the blue we see the tidal debris in stars of galaxies that are small galaxies that have been broken up by our own galaxy as they continue to devour these small galaxies as they fall into our galaxy. But this is not just our galaxy doing this. Our nearest neighbor, the Andromeda galaxy, which is the second half of the local group, in this particular picture looks a rather benign story where you have a large galaxy with two small dwarf satellites like our galaxy. But if you take a very deep picture with the Keck telescope, here is what you see. In the middle we see the disk of the Andromeda galaxy, and around it you see all these streams, and these streams are stellar streams of little dwarfs that are in the same way as Sagittarius being disrupted, completely broken up, and they're falling into the main galaxy. And many of these have been found now around both our galaxies, and of the 40 odd satellites that we know, half of them are undergoing some kind of a disruption by our galaxy. So our neighborhood, local neighborhood, is by no means a very quiet place. We have our satellites going around the major galaxies, but there are very significant stresses, tidal stresses on the minor galaxies which are causing them to disrupt and be assimilated into the large galaxies. Here is another example of a system called M81. Now if you look at the optical picture of this galaxy, here is M81, which is a spiral galaxy, and a very famous neighbor, a satellite galaxy called M82, lies here. And often people thought from this nice optical picture that they are very well separated and nothing is happening between them. But if you look at the other picture that we have here, and this is taken in radio of what is happening to the cold gas in this system, that's M81, that's M82, that's another galaxy, and you can see they're exchanging this gas between three galaxies altogether. So they are all interacting with each other, and gas is being pulled out of M81 by all these galaxies, all the neighboring galaxies, and you can see streams connecting them. And this is streams made out of cold gas that emit the 21 centimeter line in the radio. And as a result, what happens is that this M82 is one of the most spectacular starburst galaxies in the universe. This whole tidal stress due to the bigger galaxies is causing this to form stars in a very spectacular way. The star formation rate in this galaxy is 50 times more than the star formation of the giant galaxy per unit mass. And so this is amazing effect of the interactions between galaxies. So we already said that galaxies interact with each other, and our own galaxy, the Milky Way, will interact very closely with our neighbor, the Andromeda Galaxy, and even merge with it in the future. But let's see how this happens. What is the evidence of this? Here's one of the most famous examples of interacting galaxies that we see in the sky. They're called the mice because these two galaxies look like two mice playing with each other. But NGC 4676 is a combination of two spiral disk galaxies that are in the process of very closely interacting and so pulling out stars from each other, and in the process they're going around each other and then eventually merging. Now, how do we know that that's what's happening? And this is because people have done simulations where they've taken two disk galaxies with dark matter, stars, gas and dust all together, and then made them interact to produce a system that looks like this. There are many such simulations, and we'd see one of them. But before that, I want you to appreciate why we have galaxies collide with each other in the universe. And this can be calculated in very simple terms, using a very simple argument that we also use in the kinetic theory of gases when we work out the pressure of a gas. The same argument, which is known as two-body relaxation. Let's look at how frequently two stars collide as opposed to how frequently two galaxies collide. Now, say you have two stars, and your definition is that two stars will collide if their centers come close enough such that the distance between them is the diameter of each star, right? If that happens, then we call it a collision. If the two stars are separated by a distance larger than that, then it is not a collision. Okay? Now then, as a single star moves around, as a single star moves through a distribution of stars, you have lots and lots of other stars that are around it, which all have the same diameter d, and you can define a cylinder which has a diameter 2d such that the star can go through this cylinder without colliding with any other star. If, for example, any of these stars are within this cylinder, any part of the star is within the cylinder, then this star will collide with them, right? So the assumption is that a star, as it moves along, there is a cylinder around, a cylindrical space around it, such that there are no other stars that have any part of them within that cylinder. And as one of those stars come within that cylinder, it will collide with this star. And what we want to do is to find the mean time between two such collisions. Imagine that the number density of stars around our test star is the number Nd. That's the density, number density of stars. Okay? And imagine that sigma is the cross-sectional area of a star, which means that it is the area that it presents to all other stars. If its mean speed is v, then we can work out that inside this cylindrical tube, which has a diameter 2d, its total number of stars that will be inside that tube will be Nd times sigma times the average velocity times a particular time interval, which we will call delta t, and that is the time in which it moves between one collision to another, right? This is the mean time between two collisions, and this will happen when another star comes inside this cylinder. The mean collision time then comes from this argument, comes to be 1 over sigma, which is the cross section, which we can say now to be pi d squared, times the number density of stars times the average speed. Now, if we do this and we take the mean speed of each star and multiply by the collisional time, the time interval, then the actual distance between two collisions we can define as the mean free path, just like we do in the kinetic theory of gases, the mean free path, which is the mean path, the mean length between collisions, and that's given by this expression. We can calculate this if we can find out what the mean number density of stars is in any given environment, what the typical size of these stars are, and that's it. So we can do this calculation for stars. We can take the size of our sun to be a typical star and a typical density of stars as we see in the neighborhood of the sun, which would be 1 per cubic parsec, because I said that the mean distance between stars is about a parsec, and then this collisional time comes out to be about 10 to the power 18 years. That means for a typical star, the time between collisions is much, much, much larger than the age of the universe. Does that mean that stars don't collide? That is not true, because in any galaxy there are 10 to the power 12 stars. So even if the probability of collision for each star is 1 in 10 to the 18, you will always find some stars that might collide with other stars. But that is a rare event. Also, in very dense environments like globular clusters, for example, where the number density is much higher than the average number density, such collisions will always occur. And we now know that, for example, the formation of binary stars often happen because stars come very close to each other and get trapped in each other's gravity. So even if they don't collide, they can get very trapped into a binary system by coming very close to each other, and the probability of that is slightly more common than the collisional probability, but can be found in such an argument. Now, if you do the same thing for galaxies, what you have to do is to find the average density of galaxies in the universe, the average size of the galaxies, which we've already talked about. And what happens is that we find that the typical collisional time, the time between two successive collisions, is of the order of 10 to the 11 years, which is almost the same as the age of the universe. And this means in any given environment, even in an average environment, the chances of galaxies colliding with each other is not small at all. In fact, in groups and in clusters, in any galaxy, for any major galaxy, collisions and close interactions will inevitably happen. And this is what we are seeing around us. Even for major galaxies, we see them colliding, and for minor galaxies, for small galaxies, they are merging with these bigger galaxies. So when galaxies closely interact with each other or collide, what happens is that mostly the stars don't collide because of the argument we just went through. What might happen is that the galaxies have this gas that can come out of the galaxies and interact with the gas with the other galaxy and form hot intergalactic gas. And what could also happen is that due to this close interaction, you can have rapid star formation and lead to starburst galaxies. We gave you an example. Here, for example, is a picture of M82, which I have showed before, which is a small galaxy that due to this interaction, the interaction between these two galaxies, M81 and M82, has formed a starburst galaxy. So here is an animation that shows what's going to happen to our galaxy and our nearest neighbor, the Andromeda galaxy, which we can see is coming towards us at a speed currently of 123 kilometers per second, and it is, as I've said, 0.7 megaparsecs away. Now there is a view that it could be that the two galaxies might not come together, but move around in an orbit and never really merge. But a while ago, I wrote a paper to show that these two galaxies don't have that kind of angular momentum, and then they will crash into each other and merge. This is how we ended the paper, by saying that this leaves us with the rather discomforting conclusion that as the two galaxies merge, most of the inner parts of the galaxy, including our Sun, might not be saved from the merger with Andromeda after all, and this merger will happen in another 4 billion years. Now, as I said before, when the two galaxies merge, the stars will not collide with each other, and so our Sun might be saved from being merged with another star, but there will be significant tidal stress on every solar system, and the planets and the stars might be affected in a big way. Here you can see what will happen to the two galaxies which started off as disk galaxies, and they in the first pass are going to pass each other in about 4 billion years and then come back because of their mutual gravity, and you can see the various arms and tidal features that will result from it. And in the end, all the stars and the gas and the dust and the dark matter along with it, which we don't see in this simulation, will be merged into one single galaxy. Now remember, these two galaxies have their satellite galaxies with them, and they will also be merged along with them into one galaxy. Now for the interacting galaxies known as the mice, the people who have done the simulations to show how such structures can be produced also start with two disk galaxies, one slightly smaller than the other. And as you can see, as time progresses, these two disk galaxies go around each other and start merging, causing very spectacular structures within the disks of each other. Eventually, the smaller galaxy comes in and merges with the large galaxy. But the tidal streams of stars that are ejected from this system span a very large distance, which looks exactly like what you see in the observed image from the Hubble Space Telescope. And the two playful mice have now merged into one single galaxy.